What if the laws of physics themselves contain a hidden message written across the fabric of space and time? A pattern so uncanny that it makes you wonder if someone or something deliberately set the knobs of reality. Imagine finding an equation etched into the cosmic microwave background, a string of numbers and constants that should never align yet do. For decades, conspiracies have whispered about secret experiments at particle accelerators that saw glimpses of code in the quantum foam, about radio signals that, when decoded, reveal ratios of fundamental forces that look like a signature. In dark corners of the internet, you will find diagrams linking the size of the universe to the mass of the proton, suggesting that the cosmos is a vast simulation calibrated by an unknown architect. The most terrifying claim of all is that physics itself offers a proof that the universe must have a creator, a terrifying physics proof that can shatter your sense of reality. Could the fine details of our universe be evidence of a cosmic designer, or is the truth even stranger than any myth? Keep listening, because what you are about to discover will change the way you see everything around you. Welcome to Deep Space Secrets. Make sure you subscribe, turn out the lights, and prepare yourself for a journey through the deepest mysteries of physics and cosmology. Tonight we will explore the terrifying argument that the fabric of reality has been precisely arranged. And then we will peel back the myth to reveal the raw science underneath. Consider the strength of gravity measured against electromagnetism. If gravity were only slightly weaker relative to electromagnetism, stars like our sun would be significantly colder. They would never explode as supernovae, and the heavy elements needed for life would never form. If gravity were slightly stronger, stars would burn through their fuel quickly, be smaller and short-lived. Now think about the strong nuclear force that binds protons and neutrons together. If it were stronger by more than about 50%, almost all hydrogen would have been burned in the early universe. If it were weaker by a similar amount, nucleosynthesis in stars would be so inefficient that only hydrogen would remain, and there would be no carbon or oxygen. Even smaller deviations would disrupt the delicate triple alpha process by which stars forge carbon. Physicist Fred Hoyle once noted that the energy levels in carbon had to be exactly right, or carbon would not exist at all. The masses of the up and down quarks, the lightest quarks, are also finely tuned. If their difference were changed, the stability of protons and neutrons would change dramatically, leading to a very different universe. And the electron mass is roughly 10 times smaller than that difference. Alter it, and chemistry would be unrecognizable. Then, there is the strength of the weak force. If it were weaker by a factor of about 10, there would have been so many neutrons in the early universe that hydrogen would have been depleted, and stars like the sun would not exist. A stronger weak force would cause other catastrophic consequences. The cosmological constant, which describes the energy density of empty space, is also surprisingly small. Theoretical calculations predict it should be 50 or even up to 120 orders of magnitude larger than the observed value. If it were only a few orders of magnitude larger, the repulsive effect of vacuum energy would have prevented galaxies from forming. If it were negative, the universe would have quickly recollapsed. The density of the early universe had to be extremely close to a critical value. If it had been slightly larger, the universe would have recollapsed before stars formed. And if it had been smaller, structures like galaxies and stars would never have condensed. The relative amplitude of density fluctuations, represented by Q, is roughly 2 times 10 to the minus 5. If Q had been an order of magnitude smaller, the universe would have remained nearly smooth and structureless. But if Q had been larger, galaxies would have formed so quickly that everything would have collapsed into black holes. Even the entropy of the universe at the beginning must have been extraordinarily low, occupying only 1 part in 10 to the power of 10 to the power of 123 of the available phase space. When you lay out these coincidences, it is easy to see why some people suspect intentional design. But before we run to metaphysical conclusions, consider the story that modern cosmology tells us. General relativity predicts that if we trace the expansion of the universe backwards in time, the density and curvature of space-time increase until they reach a singularity where the known laws of physics break down. Roger Penrose proved that under broad conditions, such singularities are unavoidable for universes containing classical matter. Alexander Friedman's solutions showed that an expanding universe goes back to an initial singular state. Yet early cosmologists hoped that including inflation or exotic physics could avoid a beginning. In the early 2000s, Arvin Borde, Alan Guth, and Alexander Vilenkin proved a theorem that shook the field. Known as the Borde-Guth-Vilenkin theorem, It states that any universe which has been expanding on average must be geodesically incomplete in the past. In simple terms, if the average expansion rate of the cosmos is positive along any world line, then that line cannot be extended infinitely into the past. The past must end at a boundary. The theorem is robust. It applies regardless of the details of gravity, matter, or even whether general relativity holds. Inflationary models, cyclic models, open or closed universes all fall under its scope as long as they expand on average. This result seems to imply that there was a beginning of the universe, a past boundary that physics cannot cross. Many have heralded this as proof that the universe must have a cause, and thus a creator. Some theologians argue that if the universe began to exist, it must have been brought into being by an external agent. But the story does not end there. If you discovered that space and time themselves had a beginning, would that change your beliefs about a creator? Tell me in the comments down below. Modern physics offers a counterintuitive alternative. The Borde-Guth-Vilenkin theorem only shows that the classical description of spacetime cannot be extended indefinitely into the past. It does not rule out quantum processes at the boundary. In quantum field theory, the vacuum is not truly empty. It seethes with virtual particles popping in and out of existence, and these quantum fluctuations carry energy. Moreover, the energy of the gravitational field is negative. In a closed universe, the positive energy of matter and the negative energy of gravity can cancel to zero. That means the total energy of the cosmos could be exactly zero, allowing quantum mechanics to create a universe from nothing without violating conservation laws. Vilenkin and others have described quantum tunneling events in which a tiny closed universe pops out of a quantum vacuum and then inflates. In this picture, the cosmos is not designed or caused by an external agent, but emerges spontaneously because physical laws permit such creation. The initial conditions are random. There could be many universes with different properties. Some might expand and cool, forming stars and life. Others collapse or expand too quickly. We find ourselves in a universe compatible with life because in universes that are not, there are no observers to ask these questions. This is the anthropic principle in action. To illustrate how strange our universe is, consider the cosmological constant again. Quantum theory predicts that the vacuum energy should be enormous. Virtual particles of all types flicker into existence, creating a thrumming vacuum energy that should drive space apart. Early estimates suggested that this energy should be more than 100 orders of magnitude larger than what is observed. If the vacuum energy were that large, the universe would have blown apart before galaxies could form. Observational data reveal that the cosmological constant is not zero but extremely small, and yet it dominates the dynamics of the universe today by causing the expansion to accelerate. Physicists call the discrepancy between theory and observation the cosmological constant problem. Some propose new physics to explain why the vacuum energy is suppressed. Others suggest that the cosmological constant varies across a landscape of possible universes, and we inhabit one where it happens to be life-friendly. Either way, the smallness of the cosmological constant can be seen as another terrifying coincidence, or as evidence that we do not yet fully understand the quantum nature of space. Here, the anthropic principle becomes not just a philosophical curiosity, but a possible scientific explanation. If there is a multiverse, an ensemble of universes with different laws or constants, then it is not surprising that at least one of them will have parameters that permit complexity. The idea of many universes is not as fanciful as it sounds. Inflationary cosmology predicts that once inflation starts, it may never completely stop. While one region ends inflation and becomes a Big Bang universe, other regions continue inflating, spawning new bubble universes with their own physical constants. String theory hints at an enormous landscape of possible vacuum states with different values of the cosmological constant and other parameters. In this picture, we observe a fine-tuned universe not because it was chosen or designed, but because universes with incompatible constants contain no observers. In some bubbles, gravity might be so weak that no stars form. In others, the strong force might be so strong that matter is crushed into exotic condensates. We will never hear from observers in those worlds because there are none. Anthropic reasoning may seem unsatisfying, but it eliminates the need for a designer and places the weight of explanation on the statistics of the multiverse. The fine-tuning problem transforms from a question of design into a question of selection. Do you find the idea of countless unseen universes comforting or terrifying? Another key element in this story is cosmic inflation. In 1980, inflation was proposed to solve puzzles about the early universe, such as why distant regions of space have nearly the same temperature and why the universe is so flat. According to inflation, in a fraction of a second after the Big Bang, space expanded exponentially fast, far faster than the speed of light, driven by a high-energy false vacuum state. Tiny quantum fluctuations were stretched to cosmic scales, seeding the large-scale structure we see today. After a brief burst, inflation slowed to the more moderate expansion that continues and is now accelerating. Inflation not only solves cosmological puzzles but also produces a natural mechanism for generating many universes if it never fully stops. Each pocket universe can have different low-energy physics and different constants. Inflationary theory therefore ties together the fine-tuning problem, the anthropic principle, and the multiverse into one framework. Critics point out that inflation still requires initial conditions and may itself be fine-tuned, but it shifts the question from why this one universe has these parameters to why inflation happens at all. Now zoom out to the far future. The second law of thermodynamics tells us that entropy tends to increase in any isolated system. If applied to the universe, this leads to the prediction of heat death. Over trillions of years, stars will exhaust their nuclear fuel and die. Within roughly 100 trillion years, star formation will cease as the gas in galaxies is used up. After the stellar era ends, white dwarfs, neutron stars, and black holes will populate a cold universe. These degenerate remnants will gradually cool over enormous timescales. Eventually, on timescales of 10 to the power of 40 to 10 to the power of 100 years, even black holes will evaporate through Hawking radiation, leaving behind a dark, empty cosmos. In the far future, beyond 10 to the power of 100 years, the universe approaches perfect thermal equilibrium. No energy gradients remain to drive processes, no organized structures exist. The cosmos becomes a diffuse, cold bath of elementary particles. This is the heat death, a terrifying fate where time loses meaning because nothing changes. Some physicists suggest that quantum fluctuations could still create new universes or rare low-entropy patches, but from the perspective of any observer, the original universe will have become forever silent. The heat death is not evidence of design, but a consequence of the same thermodynamic laws that made life possible in the first place. Among the most striking coincidences in nuclear physics is the production of carbon in stars. The triple alpha process occurs when 3 helium nuclei fuse to form carbon. In 1953, Fred Hoyle predicted an excited energy level in carbon that had to exist for this reaction to proceed at a rate sufficient to produce the carbon we see. Experiments later confirmed his prediction. If the strong nuclear force or electromagnetic force were slightly different, the energy levels would not align and carbon and oxygen would be scarce. Without carbon, there would be no organic molecules and no life as we know it. This resonance in carbon has been cited as an example of fine-tuning and has been used in arguments for a creator. However, it could also be the result of deeper symmetries in the underlying nuclear forces that we have not yet discovered. And in a multiverse scenario, universes without this resonance simply would not produce carbon-based life. Our existence thus biases us to observe what might otherwise seem improbable. When we look at the large-scale structure of the cosmos, we find immense empty regions like the Boötes void, a sphere roughly 330 million light-years across containing only about 60 galaxies. To some, such emptiness feels like evidence that something is wrong with the universe, a glitch in the cosmic program. In fact, these voids arise naturally from quantum fluctuations in gravitational dynamics. Small variations in density after inflation grew over time. Denser regions collapsed into filaments and clusters, leaving behind vast voids. The presence of these voids does not point to a creator or a simulation, but to the power of gravity acting over billions of years. Still, contemplating the scale of nothingness can be unsettling. It reminds us of how fragile and rare pockets of matter and life are within a seemingly indifferent expanse. Could the emptiness itself be part of the answer to why we are here? Or is that just our minds seeking patterns where none exist? Do you think the apparent emptiness of the cosmos hints at deeper meaning? Or is it simply a byproduct of physics and chance? Let me know your thoughts in the comments. The uncanny alignments do not stop there. The difference between the masses of the up and down quarks governs the stability of protons and neutrons. A tiny change could make hydrogen unstable or prevent the formation of deuterium, killing stars before they ignite. The electron's mass relative to the quark masses ensures that chemistry is complex, yet stable. The relative strengths of the 4 fundamental forces determine the sizes and lifetimes of stars, the structure of atoms, and the geometry of planetary systems. Even the amount of dark matter seems tuned. Too little, and galaxies could not form. Too much, and galaxies would collapse quickly. Some cosmologists think that the density of dark matter may be selected anthropically as well. Then there are cosmic events that threaten life. Gamma-ray bursts release more energy in seconds than our sun will emit in its lifetime, and could sterilize planets within 200 light years. At least one mass extinction on Earth may have been triggered by such a burst. Supernovae within a few tens of light years would strip away the ozone layer and cause mass extinctions. Fortunately, our neighborhood lacks nearby stars likely to explode soon. The fact that our planet has survived billions of years without being wiped out by cosmic radiation is a combination of chance and shielding by the magnetic fields of Earth and the Sun. Some proponents of design arguments point to the Born-Guth-Vilenkin theorem as proof that the universe requires a cause, while citing the fine-tuning of constants as evidence of a cosmic engineer. Yet alternatives abound. Loop quantum cosmology replaces the Big Bang with a big bounce, connecting a contracting universe to our expanding one through quantum gravity effects. In this view, there was no singular beginning at all, only a transition from an earlier phase. Other models propose that time is emergent and that there was no before the Big Bang. Even if a quantum bounce or emergent time removes the need for a beginning, the question of why the laws of physics are such as to allow these processes remains. The multiverse might answer by brute statistics, but there may also be deep principles that force the constants to take the values they do. Perhaps symmetry and mathematical consistency leave no room for variation. Maybe we are on the verge of discovering a unified theory that uniquely determines all parameters, making fine-tuning a mirage. Or perhaps we will never know. The absence of a final answer does not equate to evidence for a designer. It is an invitation to continue exploring. Think about the heat death scenario again. The universe will pass through eras: the stelliferous era of bright stars, the degenerate era of remnant cores, the black hole era, and eventually, the dark era. On such timescales, our entire history is less than the blink of an eye. The second law means that the universe will move inexorably toward a state of maximum entropy where nothing happens. Yet it also allowed the early universe to start with low entropy, enabling complexity to form. Roger Penrose has pointed out that the probability of a low entropy initial state like ours is unbelievably tiny, perhaps 1 part in 10 to the power of 10 to the power of 120. But improbable events happen all the time in a vast cosmos or multiverse. We do not need to invoke design to explain a rare event if there are sufficient trials. The bigger and older the multiverse, the more likely that improbable configurations will occur. Our existence may be the result of staggering odds played out across an unimaginably large ensemble. The awe we feel when contemplating these numbers can be as profound as any religious experience. As we come to the end of our journey, the terrifying physics proof that the universe has a creator dissolves into a different kind of wonder. The fine-tuning of constants is real. The Born-Guth-Vilenkin theorem suggests a boundary, and the cosmological constant problem exposes gaps in our understanding. Some see these as signposts pointing to a designer. Others see them as hints of a deeper, more beautiful theory yet to be uncovered. The quantum vacuum may spawn universes without cause. Inflation may generate a multiverse where every possibility is realized, and the anthropic principle may explain why we observe such a hospitable cosmos. Whatever the true explanation, the scientific truth is more startling than any conspiracy. We are part of a universe that is fine-tuned for life, or selected for observers. We are here because the laws of physics permit our existence, not because they care about us. Yet the very fact that we can ask these questions, that a collection of particles can contemplate its own origins, is miraculous enough. As you turn off this video and stare into the dark, remember that the universe is vast, ancient, and perhaps infinitely varied. Whether or not there is a creator, the cosmos is stranger than anything our ancestors imagined. Sleep well if you can, but do not expect the universe to lull you into comfort. Good night. There is another perspective on why the universe seems tuned for life. Perhaps life is not as inevitable as we assume. The Fermi paradox asks why, given billions of stars in our galaxy and billions of potentially habitable planets, we have not been contacted by extraterrestrial civilizations. One answer comes from the Gaian bottleneck hypothesis. Researchers propose that early planetary environments are so unstable that nascent life must quickly evolve to regulate greenhouse gases like water vapor and carbon dioxide. On Earth, Microbes altered the atmosphere by producing oxygen and sequestering carbon dioxide, eventually stabilizing the climate. But on planets where life is too slow to modify its environment, the climate spirals out of control. Venus experienced a runaway greenhouse effect. Mars lost its atmosphere and water. The Gaian bottleneck suggests that extinction is the cosmic default for life on rocky planets. If life fails to become a planet-wide regulatory system quickly enough, it is wiped out. That means that habitable planets may remain sterile, or life may flicker briefly before disappearing. In that case, the rarity of surviving biospheres is not evidence of design, but a reminder of how precarious life is. Even if life does emerge and endure long enough to regulate its environment, more hurdles remain before intelligence can arise. New research suggests that plate tectonics may be critical for the evolution of complex life. On Earth, the movement of tectonic plates recycles carbon, distributes nutrients, and shapes continents and oceans. According to a study, complex organisms appeared on land only after modern plate tectonics began about 600 million years ago. The grinding motion of Earth's crust supplies fresh nutrients, drives volcanism, and maintains a stable climate. Planets without plate tectonics may stay in a stagnant lid state, preventing nutrient cycling and stalling biological innovation. The same study estimates that plate tectonics may operate on as little as 0.003% of rocky planets, or at most, 0.2%. Earth may therefore be extraordinarily special not because of design, but due to geological chance. This rarity influences the Drake equation and may explain why technological civilizations are sparse. Some people point to anomalies in the cosmic microwave background radiation as hints of a cosmic architect. The so-called cold spot is a region in the afterglow of the Big Bang that is slightly cooler than the surrounding radiation. Conspiracy theorists claimed it was an imprint of a parallel universe colliding with ours, or a glitch in a simulation. Recent research, however, indicates that the cold spot can be explained by a supervoid in the constellation Eridanus. The Eridanus supervoid is a vast underdensity about 2 billion light-years away, where matter and dark matter are 30% less dense than in surrounding regions. Photons traveling through this void lose energy through the integrated Sachs-Wolf effect, making the patch appear cooler. This explanation does not require a multiverse or a creator. It arises from known physics. The cold spot thus becomes a lesson in humility. Cosmic anomalies often turn out to be natural phenomena awaiting discovery. The quantum realm introduces yet another layer of weirdness. In quantum mechanics, particles exist in superpositions of states until an observation collapses the wave function. Some interpretations suggest that observation plays a role in bringing reality into existence. Physicist John Wheeler proposed the participatory anthropic principle, the idea that observers are necessary to bring the universe into being. According to Wheeler, we are not passive inhabitants but active participants in the universe's unfolding. In this view, the cosmos is a kind of feedback loop. Quantum possibilities crystallize into actuality only through measurement. While this sounds mystical, it does not invoke a supernatural creator. Instead, it suggests that the universe and observers co-evolve. The participatory principle challenges the notion of a universe existing independently of observation and invites us to rethink what we mean by creation. It replaces a distant designer with a dynamic interplay between physical laws and conscious beings. Whether this interpretation is correct remains debated, but it demonstrates how physics can blur the boundary between the external world and our perceptions. If there are countless bubble universes emerging from eternal inflation, one might ask how we count them. Cosmologists face the measure problem. In an infinite multiverse, every possible event happens infinitely many times, making probabilities ill-defined. Different measures yield different predictions. Some measures favor universes where the cosmological constant is tiny. Others predict that typical observers are Boltzmann brains, self-aware fluctuations popping out of random thermal noise. To avoid such paradoxes, physicists search for a measure that gives sensible results. The measure problem does not point to a creator, but it underscores how unresolved the science is. If we cannot even define probabilities in the multiverse, it becomes hard to draw conclusions about fine-tuning. The lesson, again, is that the absence of a complete explanation is not evidence of design, but an opportunity for further inquiry. Another line of research explores the idea that space-time itself might be emergent. In some quantum gravity theories, space and time arise from entanglement between fundamental bits of information. The emergent space-time picture suggests that the Big Bang was not a classical event, but a phase transition in a more fundamental quantum system. In loop quantum cosmology, the Big Bang is replaced by a big bounce, connecting a contracting universe to our expanding one. In string theory, the universe's initial state may have been a highly symmetric configuration that underwent spontaneous symmetry breaking. These ideas remove the singularity and the need for a metaphysical beginning. They imply that our universe is one phase in a larger, perhaps timeless framework. The emergence of space-time from quantum entanglement is not only a radical departure from classical cosmology. It challenges our intuition about creation. It suggests that asking what happened before the Big Bang might be like asking what is north of the North Pole. There may be no before, only different regimes of a deeper theory. Before we close, reflect on the implication of all these ideas. Fine-tuning may be real, but so are the selection effects of the multiverse, the Gaian bottleneck, the rarity of plate tectonics, and the staggering expanse of cosmic time. The Bode-Guth-Vilenkin theorem suggests a boundary, yet quantum cosmology offers bounce models. The cosmological constant problem is unresolved, but there may be deeper principles at work. Quantum mechanics hints that observers participate in reality, but that does not mean the universe depends on a supernatural mind. Instead, the universe seems to produce mind from matter, and then invites mind to contemplate matter. Perhaps the most terrifying aspect of physics is not that it proves the existence of a creator, but that it shows how unnecessary such a creator is. Nature might be self-contained, self-organizing, and self-explaining, or it might be part of a deeper level we have yet to glimpse. In either case, the laws of physics govern, indifferent yet hospitable. They allow galaxies to form, stars to shine, planets to persist, and consciousness to arise. They also allow black holes to evaporate, universes to end, and new universes to begin. When you lay awake at night pondering whether there is a cosmic engineer, remember that the universe is already more alien and more magnificent than any mythology. Its terrifying beauty is proof that reality itself surpasses our imagination. Good night, and let the mysteries of the cosmos haunt your dreams. In recent years, another idea has captured the popular imagination, the notion that our universe might be a simulation. Philosopher Nick Bostrom argued that if advanced civilizations can run ancestor simulations, then it is likely that we are inside one of the many simulations rather than the lone, real universe. Conspiracy theories thrive on this idea, pointing to numerical coincidences and glitches in physical constants as evidence. However, no experiment has yet detected any sign of the computational lattice or pixelation that a simulation might produce. Digital physics models that treat the universe as information processing systems are speculative and untested. Even if our universe were a simulation, it would still obey consistent physical laws set by the simulator. The existence of a simulation would not be proof of a metaphysical creator, but rather evidence that physics continues at a higher level. The irony of the simulation hypothesis is that it removes the need for a supernatural designer and replaces it with programmers within a material universe. Thus, invoking simulation as proof of a creator merely pushes the question back one level. Among the constants that have puzzled physicists is the fine structure constant, a dimensionless number approximately equal to 1 divided by 137. It sets the strength of electromagnetic interactions. If it were slightly different, the chemistry that underpins life would be vastly altered. The ratio of the proton mass to the electron mass is another dimensionless constant that affects the stability of atoms and the spectrum of molecules. Some theories suggest that these constants may change over cosmic time, but observations place tight limits on any variation. The values we measure appear fixed, and their particular magnitude has inspired both awe and speculation. Once again, these numbers could be the result of deeper theoretical relations we do not yet understand, or could vary across a multiverse. Their uncanny values invite poetic interpretations, but they are not proofs of intelligent calibration. The study of black holes has revealed another connection between physics and information. Stephen Hawking discovered that black holes radiate thermal radiation, implying that they have entropy proportional to the area of their event horizon. This leads to the information paradox. What happens to information that falls into a black hole if the hole eventually evaporates? One possible resolution comes from the holographic principle, which suggests that all the information in a region of space can be encoded on its boundary. In string theory, The ADS/CFT correspondence demonstrates that a gravity theory in a bulk space can be equivalent to a quantum field theory without gravity on a lower dimensional boundary. These ideas hint that our three-dimensional universe might be described by a two-dimensional theory at its edge. Although the holographic principle is sometimes presented as evidence that the universe is a code or simulation, it is actually a deep mathematical insight about quantum gravity. It does not imply the presence of a divine programmer. Instead, it reveals that space-time and gravity may emerge from more fundamental quantum degrees of freedom. The resolution of the black hole information paradox, still under debate, will not prove a creator but will teach us about the unity of information, space-time, and quantum theory. Do you think the simulation hypothesis makes the idea of a creator more plausible, or does it simply swap one mystery for another? Leave a comment with your perspective. After exploring conspiracies, proofs, and counterproofs, one last thought remains. If the universe were designed for life, it is a strange design. Stars explode as supernovae, gamma-ray bursts sterilize galaxies, black holes swallow light, and entire worlds are rendered uninhabitable by runaway greenhouse effects or atmospheric loss. Most of the cosmos is lethal vacuum, scoured by radiation and pierced by cosmic rays. Even on Earth, natural disasters like mass extinctions show that life is constantly under threat. If this is a garden built for humans, it is a garden filled with thorns. The cosmic violence we observe is consistent with a universe indifferent to our survival. Yet within this indifferent expanse, pockets of life arise, persist, and even wonder. There is still one more layer of cosmic mystery to ponder. Beyond the glow of the microwave background, beyond the ghostly neutrinos that stream through us from the first seconds after the Big Bang, lies a background of gravitational waves and neutrinos that we have only begun to glimpse. Neutrinos are nearly massless particles that barely interact with matter. They decoupled from the primordial plasma roughly 1 second after the birth of the universe and have been streaming through the cosmos ever since. Every second, trillions of these particles pass through your body without leaving a trace. They carry with them a record of the universe when it was less than a heartbeat old. Detecting this cosmic neutrino background would open a new window on the earliest moments of creation. There is also a rumored sea of gravitational waves, ripples in space-time produced by cosmic events and by inflation itself. The first detection of gravitational waves in 2015 confirmed that black holes merge and shake the fabric of space-time, but a stochastic background would tell us about processes that occurred long before stars existed. These backgrounds are not messages from a designer but fossil fields of the cosmos. They speak of a universe governed by general relativity and quantum mechanics, a universe where even empty space is alive with vibrations. As detectors improve, we will hear whispers from epochs that have until now been silent. The fact that the universe contains such hidden symphonies waiting to be heard is more wondrous than any mythical code. It means that the story of the universe is written not in secret signatures but in the language of waves and particles. Our task is not to decode a deliberate message but to listen carefully to what the cosmos is telling us.